Late on Sunday night, July 19th into July 20th, 2026, the seafloor off the northern tip of Vancouver Island let go. A magnitude M5.6 earthquake struck at 11:41 p.m. Pacific time, roughly 219 kilometers southwest of Port Hardy, at a depth of about 10 kilometers beneath the ocean floor, according to Earthquakes Canada. There was no damage, no injuries, and the agency was explicit that there was no tsunami risk. By the numbers alone, this should have been a one-line item. It wasn't, and the reason has almost nothing to do with the size of the shaking and everything to do with exactly where it happened. The quake was felt well beyond its epicenter. Earthquakes Canada logged shaking as far away as Metro Vancouver, more than 450 kilometers to the southeast, along with reports from Campbell River, about 300 kilometers off, and Port Alberni, roughly 330 kilometers away. That's an unusually wide felt radius for a magnitude 5.6 at shallow depth. And it says something specific about the material the rupture happened in. Cold, dense oceanic crust carries seismic energy far more efficiently than the warmer, more fractured continental rock under most cities. So waves that would normally get absorbed within a much shorter distance instead traveled hundreds of kilometers and still registered. The reason nobody was hurt is simpler than any of that physics. This earthquake happened in open ocean, more than 200 kilometers from the nearest town. Put the same rupture directly beneath a populated valley, and the outcome looks completely different. And there's a real, recent comparison available rather than a hypothetical one. 2 days earlier, on July 18th, a magnitude 5.5 earthquake struck at a similar depth near Satipo province in Peru's Central Highlands. It killed at least 6 people, injured more than 30, displaced roughly 300, and collapsed a colonial-era church and former convent that had stood since 1565. Local civil defense officials pointed to the widespread use of adobe construction in that Andean region as the reason the damage was so severe. Almost identical magnitude, almost identical depth, 6 dead in one case and 0 in the other. The difference wasn't seismology, it was what was standing on top of the rupture and how far away people happened to be. Within hours of any earthquake this size, seismologists produce what's called a moment tensor solution, sometimes nicknamed a beach ball diagram because of how the result looks. A sphere split into quadrants showing the geometry of the fault that broke and which direction the two sides slid. For Sunday's earthquake, that analysis pointed to 2 possible fault planes, both very steep, dipping at roughly 77 and 86 degrees, with motion that was overwhelmingly strike-slip, meaning the 2 blocks of crust slid sideways past each other rather than one riding up over the other. That detail is actually the most reassuring number in the entire dataset. A megathrust earthquake, the kind that produces a tsunami, happens when the descending oceanic plate thrusts beneath the continent along a broad, shallow-angled surface, lifting or dropping large sections of seafloor and displacing the water column above it. A steep, sideways slipping rupture does almost none of that. It's exactly why Earthquakes Canada could rule out a tsunami with confidence rather than caution. The fault mechanism itself makes clear this earthquake wasn't capable of lifting the ocean. So this wasn't the big one starting. But the honest, more specific answer is stranger than a simple no, and it requires understanding what's actually happening geologically at the northern end of the Cascadia subduction zone, because that's not the simple, single-fault system most descriptions make it out to be. Most of Cascadia is one oceanic plate, the Juan de Fuca plate, sliding beneath North America along roughly 100 kilometers of coastline, converging at about 40 millimeters a year. At the far northern end, near Vancouver Island, the clean picture breaks down. The incoming oceanic crust there isn't a single sheet. It's split into pieces, and the northernmost of those pieces is a small microplate called the Explorer Plate. The Explorer Plate is being squeezed and sheared from multiple directions at once by the Pacific, Juan de Fuca, and North American plates around it, and it subducts far more slowly than its larger neighbor, so slowly that some published assessments suggest parts of it may barely be subducting at all anymore. When different sections of the same plate are trying to move at different speeds in different directions, the plate can't behave as one solid block. It has to deform internally, bending and fracturing along steep internal faults, which is exactly the kind of near-vertical, sideways slipping motion Sunday's earthquake displayed. This isn't speculation built on top of an isolated data point. In late 2025, a research team led by Brandon Shuck, a geologist at Louisiana State University, who conducted the work as a postdoctoral researcher at Columbia University's Lamont Doherty Earth Observatory, published a study in the journal Science Advances documenting exactly this process using high-resolution seismic imaging. The team towed a 15-kilometer hydrophone array behind a research vessel, sending sound waves into the seafloor and recording the echoes. Essentially, an ultrasound of the plate boundary, gathered during a 2021 survey called the Cascadia Seismic Imaging Experiment. What they found, in Shuck's own description, was the first time we have a clear picture of a subduction zone caught in the act of dying. Rather than shutting down in one dramatic event, the plate is tearing apart piece by piece, generating smaller microplates and new boundaries as it goes. Schuck's own analogy for the broader process was blunt. Starting a subduction zone is like pushing a train uphill, an enormous effort, but once it's moving, it's like the train racing downhill, nearly impossible to stop. Ending one requires something dramatic. In his words, basically a train wreck. And that train wreck is what his team says they can now see happening in real time off Vancouver Island. The imaging revealed active tears inside the descending slab, including one section where the plate has dropped by roughly 5 kilometers relative to the section beside it, a structure running about 75 kilometers long. That 5-kilometer offset is worth being precise about because it's easy to misread. It isn't the result of a single earthquake. It's cumulative, built up gradually over an enormous span of geological time as the plate bent and fractured, not something that dropped in one catastrophic instant. Along that fault, some segments remain seismically active while others have gone quiet. And in most earthquake science, a quiet fault segment is the one that worries seismologists, because silence usually means stress is building with nothing releasing it. Here, the research team reads the silence in the opposite direction. The quiet sections most likely mark places where the slab has already fully detached and is no longer connected to anything capable of accumulating stress in the first place. The study's authors were careful to state directly that none of this changes the current earthquake risk for the Pacific Northwest on any timescale that matters to someone alive today. The tearing process advances at a few millimeters a year, slower than a fingernail grows, and Cascadia remains fully capable of producing a magnitude 8.5 to 9.0 earthquake and the tsunami that would come with it. There's a version of this story circulating that gets the implication backwards in both directions at once, treating the plate as dying as reassuring news that the hazard is fading, and treating the plate as tearing as evidence the big one is imminent. Both readings are wrong for the same underlying reason. The tearing changes the structure of the plate. It doesn't change the timeline for when the locked, still fully active portion of the megathrust ruptures. What the fragmentation does mean, more precisely, is that the northern margin is structurally messier than the traditional two-plate model implies, with more internal faults, more independently moving blocks, and more pathways for stress to build and release in ways that don't map cleanly onto the simple picture most public hazard messaging relies on. The Cascadia megathrust itself, the fault everyone actually worries about, runs the full 1,100 kilometers from Northern California to Vancouver Island, locked at depths shallower than about 30 kilometers, meaning the plates aren't sliding past each other there. They're stuck. And strain has been accumulating since the last full margin rupture, in January 1700, more than 3 centuries ago. That fault remains capable of a magnitude 8.5 to 9.0 event, with modeling suggesting a tsunami could reach the outer coast within 8 to 15 minutes, and, in worst-case local scenarios, run up as high as roughly 100 feet in some places. Whether the northern segment's unusual, fragmented structure makes an eventual rupture there more or less dangerous is a genuinely open question rather than one with a settled answer. If the Explorer plate is barely subducting at all, the strain budget stored at the extreme northern end of Cascadia may be lower than along the central and southern margin, a real, if narrow, nuance that complicates the simple, locked and loaded framing often used in popular coverage. The study's authors raised a second possibility that cuts the other way. The detached, torn sections of crust could act as partial barriers, potentially slowing or redirecting a rupture rather than amplifying it, which would make a shorter, segmented rupture more plausible at the northern end than a single, full 1,100-kilometer event running cleanly through it. That's a genuinely speculative extension of the published mechanism, not an established conclusion, and hazard researchers are actively working to fold these newly imaged structures into formal seismic hazard models now. That brings the story to the question most people actually want answered. Does an earthquake like Sunday's tell us anything about whether the big one is getting closer? Start with an important fact about earthquake science that's easy to overlook. An earthquake can only be identified as a foreshock after a larger one follows it nearby. There is no signature in the waveform, no characteristic depth, and no distinguishing mechanical property that marks a foreshock as different from an ordinary earthquake at the moment it happens. Globally, the odds that any given earthquake will be followed within a week by something larger nearby run somewhere in the single digits, rising somewhat with the size of the initial quake, but still leaving the overwhelming majority of moderate earthquakes as isolated events. That's genuinely reassuring, but it isn't zero, and a stark counterexample from just weeks earlier shows why the question can't be waved away entirely. On June 24, 2026, Venezuela was struck by a magnitude 7.2 earthquake, followed just 39 seconds later by a magnitude 7.5, a sequence that killed more than 1,700 people. A large earthquake following an even larger one in short order is rare. It isn't impossible. There is a concrete, checkable way to watch this specific situation. rather than sit with vague unease, and it comes down to where the aftershocks go. If seismic activity in the coming days stays clustered near Sunday's epicenter, out on the oceanic plate itself, that points to an ordinary event releasing stress built up inside a deforming slab, and essentially closes the story. If aftershock activity instead migrates eastward, toward the subduction front and the fully locked interface running beneath Vancouver Island, that would be a meaningfully different signal, suggesting stress is being redistributed toward the locked megathrust rather than dissipating locally, and would warrant real attention. That's not a subjective judgment call. It's a pattern anyone can track on public earthquake maps over the coming days by watching which direction new activity clusters. There's also relevant precedent from this same corner of the world that leans toward reassurance without erasing the uncertainty entirely. In April 2014, a magnitude 6.4 earthquake, carrying roughly 16 times the energy released on Sunday, struck this same general region and produced an extensive aftershock sequence that researchers later analyzed in detail, uncovering a previously unmapped roughly 40-kilometer fault inside the Explorer plate. That sequence's largest aftershock arrived about 13 minutes after the main shock, and the pattern of hypocenters showed the subducting plate bending and deforming in a direction nearly perpendicular to its expected subduction path. Evidence of the same kind of internal plate deformation now documented more broadly. That 2014 sequence, 16 times stronger than Sunday's earthquake, did not trigger any activity on the Cascadia megathrust itself. On the specific physics of whether Sunday's rupture could nudge the megathrust any closer to failure, the honest answer requires acknowledging that earthquakes do change the stress on nearby faults, sometimes pushing them closer to failure and sometimes further away. And that seismic waves can occasionally trigger activity on faults far from the original rupture that are already sitting right at the edge of failure. But scale matters enormously here. A magnitude 9 earthquake releases roughly 126,000 times more energy than a magnitude 5.6. The stress change from Sunday's rupture is concentrated around its own relatively small footprint, while the Cascadia locked zone extends for hundreds of kilometers. A small perturbation at one end of that enormous system doesn't meaningfully load the whole thing. If the megathrust is close to failure at any given moment, it's close because of 326 years of steadily accumulating strain, not because of one moderate sideways slip out on the fragmenting oceanic plate beside it. Strip away both the alarm and the reassurance, and what's left is this. The Explorer plate is being pulled downward while simultaneously getting pushed and sheared sideways by everything around it, and because different parts of it move at different speeds in different directions, it has no choice but to deform internally. On Sunday night, one of its steep internal fractures took on more stress than it could hold, and it broke. That's what the evidence says a magnitude 5.6 earthquake, with this specific mechanism, in this specific location, most likely represents. The ordinary signature of a plate coming apart, not a countdown to something larger. The genuinely unsettling part isn't that the big one has started. It's narrower than that. Scientists can now image the northern end of Cascadia in enough detail to watch it disintegrate in real time, and can even project that disintegration forward across roughly the next million years. But they still can't say for certain what this newly fragmented structure will do to a megathrust rupture that might begin tomorrow, whether the torn sections act as barriers that stop a rupture from spreading north, or as boundaries where a segmented rupture could instead begin. That question doesn't have an answer yet, and the only way it gets one is by watching patiently which way the next several days of aftershocks decide to go.